Our last topic about the Fourier analysis is that is the Fourier transform. Okay, so for the Fourier transform, remember when we learned about Laplace transform last semester, we have this form, minus st, e to the minus st. Now we just restrict this s domain, this s, to the imaginary axis. So to the imaginary axis, I have minus I omega. This is your Fourier transform. We will use the Fourier transform a lot because sometimes when you take the transform, it is from one domain, for example, like time domain, to the Fourier domain. And in Fourier domain, then we can analyze their spectrum. Or sometimes in time domain, it is really complicated, hard to analyze your signals. Then when you do the transform to the Fourier domain, it is easier to see your spectrum or probably to analyze it. Especially now in our baseband, we have a lot of frequencies, like my sound or other sound together. Then we have so many frequencies on the baseband. Then how can I retrieve or extract one of the frequencies? One way is that using the Fourier transform, you can retrieve or extract the frequencies that you want. So when we talk about the properties, some of the properties of the Fourier transform, you will also see that. First, let's see just see the definition of your Fourier transform. F is piecewise continuous, and the integration is finite. The F is finite because the integration exists. Then what is the Fourier transform? Your function times e to the minus I omega t. And for the abbreviation, sometimes we write in this form, okay, f omega. And then inverse Fourier transform. I have the function in frequency domain. And how can I get back to our time domain? So we will also see the definition of your inverse Fourier transform later. Okay. So now, any f integral by f has the complex Fourier integral. Okay, so we can express this function in the Fourier integral. And we have the coefficient. We know how to express the coefficient. So we know how to express the coefficients, then bring this back to our Fourier integral. Okay, so this is a c omega. And then you rearrange that f1 over 2 pi. And this is our Fourier transform of f. So this is the idea of the inverse Fourier transform. Okay, so again, I have a function f by the Fourier integral, complex Fourier integral. We know how to express that. Okay, we just done this, and to find the coefficient. So here's the coefficient. So bring this back to our coefficient. And here you can see that, especially for this part, you can think about this as a Fourier transform of your function f, because this is our definition. So f of t in time domain, I can express in this integration, and this is the concept of our inverse Fourier transform. Given the f in frequency domain. Then we take the integration to get the Fourier transform. To get the function f. So this is the formula. Okay, exactly the same here. Then we call that f are the Fourier transform pair. Every time I have a function of f in time domain, I can get the function in frequency domain. You can check the table, or we use the formula to find your function in frequency domain. Once you have a function in frequency domain, then taking the inverse Fourier transform, we can get the function in time domain. Okay. If you first time hearing this transform, then just first follow the definition. We have a transform, Fourier transform, and this is the formula for a Fourier transform. Okay. So first, let's see. I have a function. Before 0, times 0, that's 0. After that, I have a value. Remember, what is this? Before 0 is 0, and after 0, time t greater than 0, then I have a value. We can express this function using the Heaviside function, or we say step function, to re-express that. This one, I can write it down as h of t e to the minus at, and then we say a is greater than 0. This is called Heaviside function. Or sometimes you will say this is also called step function. H of t is either 0 or 1. So when t is less than 0, that's 0. And when t is greater than 0, that's 1. So if we plot this function f, before 0, that's all 0. And then, too big. Fine. Before 0, that's all 0. Once t is greater than 0, it's an exponential. It is finite, as you can see, when you take the integration. So since the integration exists, then what is the Fourier transform of this function? So this is a Fourier transform. I have a function times e to the minus I omega t dt. I don't have a value when time is less than 0, so integration from 0 to infinity. E to the minus at times e to the minus I omega t dt. So we have minus 1 divided by a plus I omega times e to the minus a plus I omega t. T is from 0 to infinity. and this is 1 divided by a plus I omega. So that means the Fourier transform of this function is 1 over a plus I omega, and a is greater than 0. That also imply, or that also means the inverse Fourier transform of one over a plus I omega. We write it down the inverse 1 over a plus I omega. This is the Heaviside function times e to the minus at, and a is greater than 0. All right. If you see some textbooks in different area, you may have a different definition or the notation. So here, you may see that actually the general form, the Fourier transform, we have the coefficient a and the integration minus I alpha omega t dt, and the inverse Fourier transform, will be b and the integration f times e to the I alpha omega t d omega. So in our class, we choose alpha equals 1 and a equals 1, and also b equals 1 over 2 pi. You may see some books, or like physics books, some other uses either alpha equals 1 and your a and b are both 1 over square root of 2 pi. Or sometimes you may see alpha equals 2 pi and then a and b are 1. But overall, they still call the Fourier transform pair. Okay. But you need to choose. You cannot just have a combination of these three. Okay. You can either choose this one or the second or the third. And then later on, normally some common used functions you derive many times, then you can remember. Or you just check the table. And also in our exam, I will give you some table. You can use the table to find the Fourier transform. Here, if I have a function 1, here's 1, then my Fourier transform will be 2 pi delta function. Delta function will be here. Okay, this is 2 pi times pike. Okay, this is in time domain, and this is in Fourier domain. So if I have a delta function in time domain, actually in Fourier domain, that's 1. Here's 1. You can see that there are some dual properties here, but in this course, we just learned some properties. If you want to know more about that, you can take the signals and systems and signals, or any advanced signal courses. And if then what is the Fourier transform of 1 over t? Like, wow, here. Those are just examples. On Wednesday, today's Monday, right? On Wednesday, I will show you some tables. Okay, we will also use that table throughout this semester. E to the minus a to the absolute t, absolute value t, we can plot that function. The function is like this. Okay, and e to the minus at squared. Okay, so for next, we need to know what is a pause function. This is a very important function. If you this class, no, but if you take the signals and systems, we will use this a lot for analyzing the sampling theory. So the pause function is that during a time period, I have a value. Otherwise, it is 0. So this function looks like here. This is time t, and then function f of t. If t is greater than a, that's 0, or less than minus a, it is also 0. But between minus a and a, I have a value, and this value here we just called a. So this is a minus, okay, minus a. And between a minus n and a, I have a value k. That is a pause function. You can see this is a pause. So for this function, using the step function or Heaviside function to express that, in this case, okay, k between minus a to a. And let's see the Fourier transform. For the Fourier transform of the pause function. So f omega it's a function times e to the minus I omega t dt. I only have a values between minus a and a. So here minus a and a. K times e to the minus I omega t dt. So you get 2k over omega times sine a omega. This is a sinc function. And then amplitude for this sinc function is k times sine a omega divided by omega. Okay. Sinc function is like this. But if I take the absolute value, just see the amplitude. This is so this is proportional to 1 over omega. So the first one, you need to know for a pause function, the Fourier transform is sinc function. Then if you have a sinc function, then your Fourier transform is a pause function. It's a pair. It's a duality. All right. So the first function that you should know. The second one is called delta function, which is mentioned here. The direct delta function. Direct delta function, just think about the pause function. When pause function, k equals 1 over 2a. And then when a goes to 0, so here this is 1 over 2a, right? For example, a is minus 5 to 5, then this k is 1 over 10. If a is minus 1 to 1, this goes to 1 over 1, 2. 0.5 to 0.5, here I have a 1 over 2a, 1. You see, this will be bigger, bigger, bigger. So when a goes to 0, this value will also go up. Okay. When this is just 0, then the value goes to infinity. Okay. So the delta function, we let a goes to infinity. Oh no, a goes to 0. About this function. So the Fourier transform of the delta function is that take the limit a goes to 0. I have sine a omega divided by a omega. And since they're all 0, you take the L'Hopital's rule. Here you get 1. Here's like O0, O0, O0. And then here's O0. When t equals 0, it goes to infinity. So actually the delta function is not a regular function. It's called a generalized function, because you see that when t equals 0, the value is infinity. Is infinite. So here is the proper definition for the delta function. When t is not 0, then it is 0. But when t is 0, this value is infinite. But if I take the integration of this function, try to find the area, right? And this integration is 1. So you need to remember this. When t is not 0, the value is 0. When t is 0, then this delta function goes to infinity. If I take, then when I take the integration of this delta function, the value is 1. Then why do we need this generalized function? For example, here, when operating another regular function, then it can pick up the value at t equals 0, which means delta function Cosine times another regular function g, and I take the integration d Cosine. What is the answer here? If t is not equal to 0, it is all 0. So whatever 0 times something is still 0. When t is 0, then I have a value. But when I take the integration, that's 1. So here, I will get g of 0. That can also imply like on Wednesday, we will also talk about some properties. If I shift then that means I have a value at A. If I shift t minus 1, what does that mean? Still 0 or infinity. But here, when t is not 0, when t is not 1, that's all 0. When t equals 1, then it's infinity. Okay, a shift by 1. Okay, so if I shift by A times this function, so if I have a function, and then for the delta function, I have values here. If I shift by A here, so I only have a value at A. So I can extract the value of our regular function at A. Let's see, why do we need to learn Fourier transform? First, we have some good properties for Fourier transform. The first one is linearity. So the two constants A and B are in the real line or in the complex line field. So this C means complex. And the linear combination of your function. Okay, if I take the Fourier transform of your linear combination of your function, actually we can take the Fourier transform first and then do the linear combination. It's called linearity. And you can also write it down. This is A times F omega plus B times F. Not F, I wonder, G. The second one is called time shift theory. If I shift in time domain, what happens in frequency domain? If I shift in time domain, then in frequency domain, I will times the complex exponential. Every time I shift by t naught, then I will generate the complex exponential in frequency domain. And since this is complex exponential, that means if I take the absolute value, you can see that if I have a time shift, in time domain, actually in frequency domain, my magnitude is still the same. I just have a phase shift. Okay. So from this equation, you should know a shift in time, then in frequency, my magnitude is still the same, but my phase will be different. Okay. We can have a quick proof. To take the shift that means you have f of t minus t naught e to the minus I omega t dt. And then you can changing variables. Not changing variables, we just add more terms on that. I have t, I get OT becomes t minus t naught. So I have f of t minus t naught. Then I get e to the minus I omega. Here I have a t minus t naught and the t minus t naught. Since I have this additional term, I should divide it by to compensate it. E to the minus I omega t naught. So they can cancel out. And that's why we have additional term, the complex exponential. What is this? The Fourier transform. Right, you can think about this as a t, and t. So this is e to the minus I omega t naught, a Fourier transform of your original function. So again, that maybe next semester or next year when you take the signals and systems, you will also learn again that if I have a time shift, that means in frequency domain, I just have a phase difference, but the magnitude is the same. So here, let's see this example. I have a function g. I have a values between 3 and 7, otherwise it is all 0. Let's plot this function first. T, and this is g of t. I have a value between 3 and 7. So suppose here's 3 and here's 7, and the magnitude is 6. How do I find the Fourier transform of this function? Oh, and also here we have a table. So you can see the Fourier transform. If I have this form, and this is my frequency domain. All right, you can also download it on NTU Core. And we will also provide this table on your exam. We know a pause function, the Fourier transform is a sinc function. Okay, we can use this. A pause function, that is this one. And then I will get a sinc in frequency domain. So this is in my pause. So to find this Fourier transform, we can also think about the pause function. Say t, and this is f of t. From -2 to 2. So the function g is the function f shift by 5 units to the right. So that function g is function f, but I shift to the right by 5 units. Right, if I shift to the right, I have a values between 3 and 7. Here is still 6. Okay? And we just done the Fourier transform of this one. Here. Okay, that is our Fourier transform. The pause function. So previously, we know the Fourier transform of my pause function. It should be 2k over omega times sine a omega. Now here we have a equals 2. And then k is the magnitude. K equals 6. This is a sinc function. Sine omega divided by omega. So now this is my Fourier transform for the pulse function. And then I shift by 5 to the right. What is the Fourier transform? So this is the Fourier transform of your function f. Shift to the right by 5 units. Shift to the right, we know that if I have a time shift, what is the frequency? What is the Fourier transform? My Fourier transform is the same. The magnitude is the same, but I have a phase change. Okay, the phase difference. So I should know that this is still 12 over omega times sine 2 omega. This will always the same. Then I have a phase difference. This phase difference is e to the minus j. What did I use? I think I use I 5 omega. Okay. So similarly, the inverse version of the shifting theory. That'll be, if in frequency domain, I just change the phase. That means in time domain, I have a time shift. All right, so now let's do this example. Okay, now you see that find the inverse Fourier transform. I have this complex exponential. Then you may think about that I may have a phase change. So then my original prototype will be 1 divided by 5 plus I omega. Right, so remember that 1 over 5 plus I omega. What is this is a Fourier transform. Then what is the time domain? How do I express that? Now, which one? Again, I have a 1 divided by 5 plus j omega. That's in our frequency domain. So in time domain, what is this? What is the equation? Which one? So first one, right? My a is greater than 0. So I should have e to the minus at times what is ut? The unit step function or Heaviside function. Okay, so I should have this one. So now we know the Fourier transform of the Heaviside function or the unit step function times e to the minus at. That is 1 divided by a plus I omega. Okay, so I have a 1 over 5 plus I omega. I should have this Heaviside function, right? So I should have h of t e to the minus at, h of t e to the minus 5t, correct? But since I have complex exponential in my frequency domain, that means in time domain I have a time shift. This is our function, and the time shift by what? By how much? Time shift by 2 to the right, right? So my t will becomes t minus 2. Here, t minus 2. Okay, here is plus 2. So I will shift to the left. So it will be t plus 2, and here will be t plus 2. Okay, because if I have a minus sign, that means I will shift to the right. But if I don't have the minus sign, then I will shift to the left. So here it becomes t plus 2, t plus 2. So this should be Heaviside function, t plus 2. E to the minus 5, t becomes t plus 2. Okay. The next one is called the frequency shift theory. If I shift, actually we learned that if I shift in time domain, then in frequency domain, I just have a phase difference. Now if I shift in frequency domain, what happens in time domain? Looks like similarly in time domain, I have for the same magnitude, but at times the complex exponential. Okay. And later on we will say that this is the modulation. Okay. So the inverse version of the frequency shift theory is, if I shift in frequency domain, then in time domain, I just times e to the I omega naught t f of t. So now let's see this example. I want to find the inverse Fourier transform, this one. So go to the table, and then let me write it down. It should be 4 times e to the I 2 omega minus 6 divided by 5 minus 3 minus omega times I. This is in frequency domain. So which one we should use? Which number? Looks like my omega is shifted by 3, right? So the original form should be like 5 minus omega. And now later on we'll change omega to omega minus 3. So I shift omega by 3. In time domain, I should have e to the I 3t. All right. Then what else? Now I also times exponential part. In frequency domain, if I times exponential part, what does that mean? In time domain, I will shift by how much? Here I will shift by 2. Right, and the original form here it should be 1 divided by a minus I omega, or plus I omega, and still this one. Yes, still this one. All right. Okay, then your time. So what is the final answer? So we know that we will use this, okay? So back to our notes. We will use equation 1, the first table 1. We need to rearrange that. 4 divided by 5 minus just plus omega minus 3 I, right? In the denominator, okay? Now in the numerator, e to the I 2 omega minus 3. Okay? All right, then you compare to our previous one. Okay, my omega becomes omega minus 3. Right? Omega becomes omega minus 3. So I shift in frequency domain. Then in time domain, I will times e to the I 3t. Keep the original one. This is our Fourier transform. This is our time domain times e to the minus 3t. And now since I have a 4 rather than nothing, so here I should have 4. Okay? Any questions for this? So there will be 4 times Heaviside function e to the minus 5t plus 2. And then we have a shift, so e to the I 3t. All right, next property, the scaling. Okay, so if I become fat at times 80, so it can be flat. Oh, my original function maybe like this. And then when a is greater than 0, then I may have a sharp one. A is less than 0, I may have a flat curve. So if I times a in time domain, then in frequency domain, I just need to do the compensation. So I divide by a. Remember the Parseval theory? The energies, either in time domain or frequency domain, they should be the same. So in time domain, if this is my energy, I find the integration, so the area is here. Then in frequency domain, I should have the same area. Okay, so if in time domain, this function become bigger, then in frequency domain, I should do the compensation, so it will be more flat. So overall, the area will be the same. So the energy is still the same. So the inverse form. If I divide by a in frequency domain, that means in time domain, I'll time this scalar back. All right, next one, time reversal. If this is my frequency transform pair, function in time, frequency in and the function in frequency domain. Now, if I flip in time domain, if I function like this, and if I flip, it becomes this one. In frequency domain, I also flip. Okay, you can bring this back to our definition. Calculating the integration, you will see that my frequency domain also reversed. Next one is a symmetry. Okay, have you thought about that? If I take the Fourier transform for this function, so here is a time domain. Now I take the Fourier transform, maybe it looks like that. This is in frequency domain, right? We have omega. But we can also think about this function as a time function. I can change that to t. And I can do the Fourier transform again. So when I do the Fourier transform, what is this? So you see that if I do the Fourier transform, then I will go back to my original function f. Okay, so in the beginning, I have a f over t, and I do the Fourier transform. And for this Fourier transform, I do the Fourier transform again. But we'll think about this function as a t function in time. I do the Fourier transform. And then in this frequency domain, you can see that this function is back to our original function, f. But now we will use the omega for your variable, for your parameter. Okay? Let's prove this. We know that, how do we get the function t? We can take the inverse Fourier transform. Okay, so for the inverse Fourier transform, it is 1 over 2 pi integration e to the I alpha t d alpha. Now, let's change the variable. Here, let's let t equals minus omega. So t equals minus omega. That means I still have 1 over 2 pi. And then f of alpha e to the minus I alpha omega d alpha. So t becomes minus omega. Then next step, I will change alpha to t. So now alpha equals t. I have 1 over 2 pi. F of t e to the minus I omega t dt. What is this integration? That is the Fourier transform, right? So this is 1 over 2 pi Fourier transform of your f of t. Okay, so now let's see this example. For the delta function, we know that the Fourier transform of a delta function means that I have 0. I only have a value at 0. Otherwise, it is all 0. Okay, this Fourier transform is 1. And then I will also think about this function as a time domain. What is the Fourier transform of that? So now, for this one function, I take the Fourier transform again. So the Fourier transform of 1, there'll be 2 pi delta function minus omega. And since we know the delta function, I only have a value at 0, so it is also equal to delta function at omega, delta function. So you can see that for this one, delta function, the Fourier transform is 1. So I get here is 1. You can see that for delta function, first delta function, the Fourier transform is 1. The area is the same. All right. I take the Fourier transform again. What do we have? 2 pi times delta function. So it is still here, but I times 2 pi. So if you take the Fourier transform twice, they'll go back to your same shape. Okay, but you have a scaling. Okay. So again, we know that if I have a delta function and then take the Fourier transform twice, I will still get a delta function. If I have a pause function, we know when we take the Fourier transform, what do we have? Sinc function, right? Then I take the Fourier transform of my sinc function, I will back to my pause function, but with a different scale. If this is 1 here, I think it will be 2 pi. If you take this function for Fourier transform, again, then you'll get the sinc function. We're going to learn another important one called modulation. Modulation means that if I have a signal in time domain, do the modulation means that I will time the cosine or even sine. And you see what happens when I have a function times cosine. When I have a function times cosine, then in frequency domain, what happened? In frequency domain, I shift to the right and shift to the left and have the magnitude half of them. So if I have a signal in time domain, then when I take the Fourier transform, I will shift my signal. Now if the magnitude is 1, here I will shift to the right for omega naught, and the magnitude, the peak will be 1/2, and also shift to the left. Okay? So that is the modulation. I will just shift to the right and shift to the left. Same thing for the sine function. Why do we need to modulate? You can see that if in a baseband, I have a signal, and maybe your voice, this is another signal. And the train station, they have a lot of background noise, I have another signal. They have a different frequencies. But in time domain, you will see there'll be a lot signals together. Then you can see that it's actually hard to retrieve or extract one of the signals, right? With the different frequencies here. But if I times the cosine with omega naught t, then I can extract those signals because they will shift to the right and to the left. So in this case, they may shift to the right, and then I have a different signals, and so on here in the left-hand side. So I can extract and analyze those signals separately, and you can do something for that. And later on, you can times the cosine, and then they will go back to your baseband. So that's why that a lot of time we need to do the modulation, because after doing the modulation, you can really analyze each signal. Okay. For example, like if you make a sound like a music, your frequency is like a 440, maybe 440, and your voice, I forgot, maybe your voice is another frequency, maybe, I don't know, 400. Because once you times cosine omega naught t, you can see I will shift to the right by your omega plus this omega naught. So that's why that we can separate that those different signals. If I have a signal cosine 20 t plus sine 400 t plus cosine 150 t. In the time domain, probably like that. Okay, but if I do the modulation, times like modulation, omega naught will be 300, suppose. So you see that when I take the Fourier transform, this signal will go to here 280, and this signal will go to minus 100, oh no, 100, and this one will go to minus 100, minus 150. So I can see those signals in different frequencies. So now I can analyze it. Okay. So that's why that we takes times cosine or sine. Normally we times exponential, but that's so expensive. You see that if I times complex exponential, I also shift in frequency. But this is very expensive, so normally that we just times cosine or sine. Okay, so for example, I have a pulse modulate signal. Pulse modulate means that I have values. Well, we know pulse, right? Only when the signal is between, for example, between minus 3 to 3, I have a value 1. Otherwise, there'll be all 0. So now if I have a cosine signal, I only want to get this part, so I can times a pulse with this signal. So it is called a pulse modulated signal. And we can plot this function. So for this function, this is f of t. And then this is a, here is k minus a. And if t is greater than a or minus or less than minus a, there'll be O0. So for this signal, with the conditions, we can rewrite this signal using the step function. Okay, so how do I write this function in terms of unit step function or Heaviside function? So the function is k cosine omega naught t. I only have a value between minus a and a, so I need to times the Heaviside function t plus a minus the Heaviside function t minus a. Okay. T plus a, that means I have a value. I have a value and minus a, that'll be O1. And now t minus a, I have a value at a, that's 1. So they will cancel out. So it is a pulse. Okay? So it is a pulse between minus a and a. And times your amplitude, there will be k. And then times cosine. We just learned that what is the Fourier transform of a pulse. A Fourier transform of a pulse is sinc function, right? The sinc function. And then, of course, that if you take the sinc function, the Fourier transform of a sinc function, you will get a pulse. So now let's consider the Fourier transform of the magnitude, amplitude k, times the pulse. That will be 2k times sinc function sine a omega divided by omega. And then think about this signal times cosine. Now if I times cosine, I know that they will shift to the right and shift to the left, and the magnitude will be half of them. So I will have this here, and the magnitude will be k over 2. And then this one will be omega naught. So omega naught plus a, omega naught minus a. Therefore, the Fourier transform of your modulated, pulse modulated signal times doing the modulation, so times cosine. Cosine omega naught t. So the magnitude will be half of that. I will get k. And then the frequency, you'll shift to the right by omega naught and also shift to the left by the omega naught. So I have a sine a, omega becomes omega plus omega naught. And then shift to the right. Why and how do I know that they will shift to the right and shift to the left if I times cosine? And now we can see the Fourier transform of a cosine function. Let's see what is the Fourier transform of a cosine function. Or we can also express cosine function using the Euler formula. Not seeing the Fourier transform of the cosine, but we just rewrite the cosine function as the complex exponential. So cosine omega naught t equals 1/2 e to the I omega naught t plus e to the minus I omega naught t. So if you have a function times cosine omega naught t, that means it is 1/2 of your Fourier transform exponential I omega naught t times your function. And the second term, 1/2 the Fourier transform of e to the minus I omega naught t times the function. And we just learned it from the shift theory in time domain. This, I will shift in frequency domain, I will shift to the left. And here I will shift to the right. Yeah, that's the frequency shift theory. So here we have 1/2 Fourier transform to the left, and then Fourier transform to the right. where is here? Okay. Any questions for this one? You will learn more when you take the signals and systems, that course. Okay. And we will use the modulation a lot. You also see more applications when you take some advanced course. Okay, if you don't have any questions, next one, the Fourier transform of a differentiation in time domain. So what is the Fourier transform of a derivative? Let's have n positive integer, and the nth derivative is piecewise continuous, and this integration exists. That means the n minus one derivative is finite. Then, if we know that the Fourier transform of the function f, we can write it down as f of omega. Then every time when I take a derivative, I will produce I omega. If it is the first derivative, I'll get I omega. If I take the derivative twice, then I will have I omega squared. If I have nth derivative, then I have I omega n to the n. Every time when you take the derivative, then you'll get or produce the I omega. Okay, so let's prove that suppose we have just one derivative. So for n equals 1, what is the Fourier transform of f prime? We can still find that by using the definition. The Fourier transform is f prime e to the minus I omega t dt. The integration by parts. So I have f of t e to the minus I omega t minus infinity to infinity. And then I have minus I omega f e to the minus I omega t dt. Then you have I omega f of t e to the minus I omega t dt. And this is the Fourier transform. All right. Suppose f for this function, we have some discontinuities at some point. Like I have a discontinuity at some point. Then what is the Fourier transform of for example, the first derivative? I still create I omega, and then I have additional term. So here we can plot this first. This is my function f. And then I have here, this is tk. So this is f of tk to the left, and also here tk to the right. So here we have a jump. This jump is, the value will be tk to the right minus f tk to the left. Now we just assume we have one discontinuity at t1. Here tk is just t1. And let's figure out what is the Fourier transform of the first derivative. So we assume only one discontinuity. So the Fourier transform of a first derivative definition integration f prime times the complex exponential. So we can separate this into two parts. One, the integration is from minus infinity to t1. And then doing the integration from t1 to infinity. I should have f prime. Okay, so I can have each. First, I'll do the integration by parts. Second, I will also do the integration by parts. So overall, I have 4 terms. So this is the first one. For the first one, I have f of t e to the minus I omega t. And t is from minus infinity to t1. And I do the integration from minus infinity to t1 I omega f of t. This is the first part. And second part, also using the integration by parts, we have f of t e to the minus I omega t, t1 to infinity, so I can combine it f of t1 minus f of t1 to the right overall and times exponential, and then the rest I have I omega doing the integration. And this is your Fourier transform. And so that's why we have I omega. Every time when you take a derivative, you will create I omega. Okay. Why do we learn Fourier transform? One of the reasons is that, well, overall for this course, we're trying to solve the differential equation, ordering differential equations, right? And from the last semester, we have already done different methods. Okay, first we check if whether this function, this differential equation is separable or linear or exact, or even it is a spatial one. With a different case, then we have the method and answer to that equation. And then we learn Laplace transform. So we can use Laplace transform to solve the differential equation. And we can also use Fourier transform to solve the equation. So here, suppose I have a differential equation, y prime minus 4y, and this is the forcing term. How do we solve or find a solution in the past? That we probably need to guess, right? We may have the particular solution, and how do we find the solution based on this part, the forcing term? And we can guess, since I have an exponential, so my answer should have the exponential term. Sometimes that's more complicated or even hard to find it. So we can use the Fourier transform or Laplace transform to do it. So here, let's use the Fourier transform and see how we find the solution. So we can apply the Fourier transform. So here I have a Fourier transform of y double prime minus 4 Fourier transform of y. Right hand side, I also take the Fourier transform. So for Fourier transform, okay, why do I have double prime? I only have a y prime. Every time when I take the derivative, I will generate I omega. So here I have I omega, Fourier transform. Maybe we'll write it down y omega. And minus 4 of Fourier transform, so I or y omega. Right hand side, you get 1 divided by 4 plus I omega. Let's see the table. We have e to the minus 4t times the unit step function. Okay. So my a is 4. So just this one. Okay. Back. So in this case, we can get the Fourier transform of y. So the Fourier transform is that is minus 1 over 16 plus omega squared. Then we can take the inverse Fourier transform to get our answer, y of t. So inverse Fourier transform minus 1 divided by 16 plus omega squared. Okay, so that's practice. How do I use the table to find this inverse Fourier transform? I have minus 1 over 16 plus omega squared. So which one? Oh, which ones are the candidates? This is the in frequency domain. Minus 1 over 16 plus omega squared. Which one? This one, right? Because I have a squared plus omega squared. Okay. Then, what is my a? A will be 4, right? So I need 4 squared plus omega squared. And then this is minus 1. But I need 2a, which means I need 2 times a. I need 8 here. Correct? I need a here, so I also need to divide by a. Okay, so this one will be minus 1 over 8, and then 4 squared plus omega squared, 4 times 2. 2 times 4. Okay? So I have additional term minus 1 over 8. And then in time domain, there'll be e to the minus 4 absolute value of t. Minus 1 over 8 exponential to the minus 4 times the absolute value of t. Okay. Now, next. And how about the Fourier transform of differentiation in frequency domain? So, what does that mean? That if I take the derivative in frequency domain, that means in time domain, I will times t. Every time I take the derivative, and I will get t. So if I take the derivative twice, then in time domain, I will times t squared. I will time t twice. So the Fourier transform of t times f over t. That means I will take the first derivative in frequency domain. If I have a t squared times the function, that means in frequency domain I take the derivative twice. So that means if I take the inverse Fourier transform of your nth derivative in frequency domain, that'll be I to the n times, and also t to the n times your original signal or function. So now let's have a proof. Suppose n just equal to 1. First, what is the Fourier transform? That's the function f times e to the minus I omega t dt. Then take a first derivative, f prime. If I take the derivative here with respect to omega, so here I have minus I t, the chain rule, f of t, e to the minus I omega t, dt. So it'll be minus I and the integration t times f of t times the exponential minus I omega t dt. So that is minus I times the Fourier transform of your t times your function. Okay, this is also the Fourier transform of this function, t times f of t. So here is the example. I want to find the Fourier transform of t times e to the minus at squared. E to the minus at squared. Looks like we don't have this one, right? Oh, we have here. Okay. So compare minus at squared and minus t squared over 2 sigma squared. So your a should be 1 over 2 sigma squared. Okay. Where? On this one. So we know the Fourier transform e to the minus at squared, that is square root of pi over a times e to the minus omega divided by 4a. Now I take the derivative. F prime omega. You take the derivative with respect to omega, we get minus 2 omega over 4a and square root of pi over a e to the minus omega square over 4a. So the Fourier transform of t times your function e to the minus a t squared, that will be I times the derivative of your Fourier transform. So it will be minus I omega over 2a and the square root of pi over a e to the minus omega squared over 4a. Next one is the Fourier transform of integral. Nth derivative of this function is piecewise continuous. And then the n minus 1th derivative exists or is finite. And I have a Fourier transform with omega 0, omega equals 0, then the function is 0. Then when I take the Fourier transform of the integration, and that means in frequency domain, I will divide by I omega. It's pretty similar to the Fourier transform of differentiation. If I take the derivative in time domain, in frequency domain, I will create one I omega. Every time I will create I omega. Now, for the integration, if I do the Fourier transform for the integration, in frequency domain, I will divide by I omega. Okay, let's quickly prove this and then we can take a break. So suppose the g function this is the g function. Okay, so overall this is a g function. Then by the calculus, g prime, what is g prime? if I take the derivative, g prime will be your function of f, right? And here, note that this function goes to 0 as t goes to minus infinity. That'll be 0. As t goes to minus infinity. And then if t goes to infinity, positive infinity, then the g is from minus infinity to infinity, f of tau d tau. So we can also rewrite this integration for f of tau, but at times e to the minus I omega t d tau, but we set omega equals 0. So in that case, the exponential term is still 1. Okay, so here is our Fourier transform. So Fourier transform of f of t, that'll be the Fourier transform of your g prime. And that is I omega times the Fourier transform of g, and this is I omega, Fourier transform of your integration of your function f. Next one is the convolution. And what is convolution? I think we just learned that a little bit before in last semester when we talk about the Laplace transform, right? But here, let's just review that what is the convolution. The definition of the convolution is I have a function and the other function, I flip and shift. So I flipped, this is my function. And my another function, maybe here, but I need to flip. So when I flip, and then I shift to the right. So I shift, I move, like windowing, move to the right. And then times my original function f. This is g. Okay, so flip and shift to the right. We can let, now we need to know that for the convolution is commutative, which means f convolve g is equal to g convolves f. So by this definition, we can let, I have just changing variables. Okay, so t minus tau, let's change the variable. T minus tau equals tau bar. So tau will be t minus tau bar. According to the definition, f convolve g, so f, this function I fixed. And function g, I will flip. So here I flip and shift to the right. Okay. So if I have a g convolves f, that means I fix g, I fix function g, and I flip f and shift to the right. Flip f and shift to the right. So here I have a t minus tau d tau. Now I will change t minus tau to tau bar. So tau will be t minus tau bar. T minus tau bar f of tau bar d tau equals t minus tau bar, d tau equals d tau bar. Okay? So here's tau bar. And you can see this and here, they are the same. So it is equal to f convolves g. So we say that convolution of f and g is commutative. Therefore, for the Fourier transform of the convolution, if I have a convolution in time domain, then in frequency domain there will be multiplication, which means the duality. If I have a multiplication in time domain, what happens in frequency domain? I have a convolution. Okay, so here, this is the convolution in time. Then I have a multiplication or the product in frequency domain or in frequency. According to this convolution theory, that means if I take the inverse Fourier transform in frequency domain, then I will get in time domain I will get f convolves g. So if I take the inverse Fourier transform of the product of two Fourier transforms f and g, that means in time domain it is a convolution. And also the inverse Fourier transform that in frequency domain I do the convolution, that means in time domain I have a multiplication. Let's prove this. The proof is quite easy. It's just changing variables. Let's see. How do we prove that? F convolves g. That is the integration because it's a Fourier transform of f convolves g. Fourier transform and f convolves g, we have the definition that is fix f and then flip g. First flip and then shift to the right. So t minus tau. And then times exponential to the minus I omega t dt. I have a d tau. We'll do the integration with respect to tau and t. We can consider to take the integration with respect to t first, and then doing the d tau. So here let's just reorder the terms inside. So here I have f of tau and g, t minus tau, and exponential. Then I have a dt first, and then d tau. So if I do the dt first, this is a function of tau, right? Nothing related to t. I can put it outside. So I have f of tau, and then g t minus tau e to the minus I omega t dt d tau. So first, what is this one? If I shift tau in time domain, what happens in frequency domain? I shift in time. In frequency, I still have the same magnitude, but with a phase difference, right? So here I have the Fourier transform of g. Then I need to have a phase difference times e to the minus I omega tau. Okay? So here I have e to the minus I omega tau g omega d tau. So I can put omega outside. F of tau e to the minus I omega tau d tau. And what is this integration? That is the Fourier transform. So we have g times f. Right, let's see this example. I want to find the inverse Fourier transform. Okay, so for inverse Fourier transform, every time that we just check the table first, we have 5 over 2 minus omega squared plus 3i omega. Looks like we don't have this. I think we need to manipulate with the denominator first. So what is 2 minus omega squared plus 3i omega? 2 minus omega squared plus 3i omega, that'll be 2 plus I omega times 1 plus I omega. So the inverse Fourier transform of 5 divided by 2 minus omega squared plus 3i omega can be written as 5 times divided by 2 plus I omega, and then 1 divided by 1 plus I omega. Now you see that I have a multiplication in frequency domain. Then what happens in time domain? Convolution. But what is the function in time domain? I have 2 plus I omega, 1 plus I omega. So 2 plus I omega, this one, right? A is 2. Then I need 5 times here. And also 1 divided by 1 plus I omega. Now the A is 1. Okay, so I should have this function in time domain. So that will be 5 times Heaviside function e to the minus 2t, and also Heaviside function times e to the minus t. In time domain, they will do the convolution. So now let's deal with this convolution. by definition, we should have 5 integration. Which one do we want to choose to fix? Let's just fix this one. H tau e to the minus 2 tau. And the other function I will flip and shift to the right. So I flip and shift to the right. Again, I flipped and then shift to the right. D tau. So we have h tau and also the Heaviside function t minus tau. What is this two? I do the product. So we need to check h tau times h t minus tau. We know Heaviside function is either 1 or 0, right? So if I have two Heaviside functions times together, have a time shift, then I still need to know when I will get 1. Okay, when I will turn on the light. So it should be either 1 or 0. So now let's just plot the Heaviside function tau, and also if I flipped and then shift to the right by t, what is this? So first, for the first Heaviside function, that's the normal. I have value 1 when t is greater than 0. Otherwise, it is 0. So here. For the second one, t minus tau. Here, my x-axis is tau. So what is a t minus tau? How did you plot this? It is not a function of t, okay? It's a function of tau. So what I just meant that for the convolution I flip, so I will flip, become this. And then shift to the right, because it's minus tau plus t. Shift to the right. So you shift to the right. So till t here. Okay? So flip and shift to the right. So this is t. Then you can see that apparently if you time these two functions together, I only have value 1 from 0 to t. Correct? So when I get 1, that means my tau is between 0 and t. Otherwise, it is 0. And you can see that this is the variable t, right? So when t is less than 0 here, then the multiplication of the product is 0. Okay? So for t less than 0, then your product is 0. When t is greater than 0, then the product is either 1 or 0. So if it is 1, that means the tau is between 0 and t. Otherwise, this is 0. Therefore, back to here. So this is either 0 or 1. Then we have 5h e to the minus 2t convolves e to the minus t. It's tau should be from 0 to t. Otherwise, the inside, the integral will be 0. E to the minus tau d tau. That will be 5 times e to the minus t times 1 minus e to the minus t. This is for t greater than 0. Or we can also write it down using the Heaviside function. Okay. Right, the last one will be the Fourier cosine transform and Fourier sine transform. We will see that in partial differential equation. So let's just take a look. What is the Fourier cosine and Fourier sine transform? First, let's see the Fourier cosine transform. This is the definition. Instead of times the complex exponential, I have a function just times cosine. Okay. So we call that Fourier cosine integral. For the Fourier cosine integral, what is a Fourier cosine integral? I have function that is 1 over pi integration from 0 to infinity and the coefficients times cosine. Similarly, then how do I find the coefficient? Times the basis. So times the basis, the function f times the basis cosine. So f times cosine then in this case the coefficients will be double of your Fourier cosine transform. All right. So in this case, if I take the inverse Fourier cosine transform of your Fourier cosine transform, that should be your function. And then 2 for the Fourier sine transform, you just have the function times sine, okay, and do the integration. Then in the inverse Fourier sine transform, there'll be two over pi Fourier sine transform times the basis. Basis is the sine function. And then here we have some properties like linearity. If I have two functions and then I want to find the Fourier sine or cosine transform, I can have the Fourier sine or cosine transform first and then do the linear combination. And for the derivatives, if I take the derivatives, remember for taking the derivatives, in your frequency domain, I will create I omega. Every time when I take a derivative, I'll get I omega. If I take the derivative twice, so I have I omega twice. 3 times, I have I omega cube. Okay, so that's why I have minus omega squared, because I omega squared will be I squared omega squared. All right, so for next Monday, we have a midterm still in Season 103, and then you have 10 questions. So for 10 questions, you may find the Fourier series. To find the Fourier series, you need to know how to find or express the coefficients. Remember that for the coefficients, because the linear combination of your cosine sine, those are the bases. So to find the coefficients, you just times or inner product, the function inner product, the basis. Then you can get your coefficient. And how do you express the Fourier cosine series and also Fourier sine series? Again, how do you express their coefficients? Okay. And then for the complex Fourier series, so for the complex Fourier series, then how do you find your coefficient? You see that if I have a question for this, there are 1, 2, 3, 4. 4 questions, then every time you need to find a coefficient. And then we talk about the Fourier integral, or Fourier cosine and Fourier sine integral. Again, you need to know how to express the Fourier integral and also find out their coefficient. And also for the complex Fourier integral, then how do you find the coefficients? Okay. When you find the coefficient, you may encounter this kind of integration, x times cosine. So how do you do this integration? We know that integration by parts. You can do integration by parts, but you need to do that twice. Or the other way, I can express cosine as the exponential using the complex Euler formula. Okay, because exponential is probably easier. But if you don't use the Euler formula, then you can see that integration by parts, here, integration by parts. Yeah, you just do the integration by parts one time. You'll get the integration of x times cosine and x times sine. But if you have x squared, then you need to do the integration by parts twice. Okay, so this is the first time. Once you have the first time, you see that I have this term. I also need to do the integration by parts again. So this is the second time. All right.